Hello. This video demonstrates implementing a 32-bit up and down counter on the TerasIC DE1-SoC board, where the four MSBs of the 32-bit counter will be assigned to four LEDs on the FPGA board. With this experiment, we'll go through designing the RTL, simulating to verify whether our design works, a pin assignment so that it map the place and route of done by the Quartus Prime application works as per our requirement, and then we'll also be performing timing analysis. That is verifying the critical path, the slack on the system, the maximum frequency the design works. So all those details we'll be verifying to see how our design works and is being implemented on the board. The objectives of this experiment would be synthesizing the design in such a way that it works on the targeted board, designing the RTL to make sure our design works as per our requirement, and also using constraints. Here in this experiment, we'll be using a timing constraint, that is making sure that our counter works as per the clock available on the FPGA board. So our design of 4-bit counter uses a 32-bit pre-counter. This is to make sure that the 4 bits that are being displayed using an LED will be visible, since our board operates at 50 MHz. If we use the 4 LSBs, then we'll not be able to view the counting on the LED. It'll be too fast for us to see the changes. Due to which we'll be using a 32-bit pre-counter and assigning the MSBs. For this design, we are using two user-provided data, which will be reset and direction. This will be controlled using switches and buttons on the FPGA. A reset, we'll be providing this input to reset the counter back to 0, where it is an active low reset. And for direction, this will help us control whether it is an up count or a low count. We are giving the sensitivity list as positive edge of the clock or negative edge of the reset. If reset is pressed, which is an active low system, the pre-count will be set to 0. If the reset is not provided, then we'll evaluate the direction. Direction we have provided as if direction the switch is thrown or switch is pressed to active high, the counter will perform up count. Else, if the switch is placed in a negative or active low position, the pre-count will be decremented or it will follow a down count. So at each cycle, we'll be assigning the 4 MSBs, bit, the 32-bit to 29th bit, or assigning it from 31 to 28 of the pre-counter to the count value. For the clock input, we'll be using the onboard oscillator, which has 50 MHz, or as you can see here, we have provided the period as 20 nanoseconds. This will be the main constraint given to the design, where we'll be mentioning it in the SDC file. Before we proceed for pin planning or assigning the pins for the input and output ports of our design, we'll have to first compile. While we are at it, here we can see the number of logics used, the ALMs. For this design, there are 17 ALMs used, and number of registers are 32, since we are using a 32-bit counter, and total number of pins is 7, where that includes clock, reset, direction, and 4 bits for count. Pins are assigned to the board using the data sheet and the pin planner. All the 4 bits of the count to LED pins, LED 0 to LED 3. A clock is assigned to the respective clock input of pin AF14, reset to a push button pin AA14, and direction to a push switch pin AE12. So based on this constraints, you can see here the pins are assigned onto the board. Once the pin assignment using the pin planner has been completed, we'll have to compile again so that the Compiler knows what are the pins and pin constraints so that it can place and route the modules accordingly. Once the compilation has been completed, we can go to programming the device, for which we'll just go here to tasks, program device. So this will open up a device programmer. Here we'll have to make sure that the hardware is matching properly. DE1-SoC board is being shown up here. Next, we'll just click auto detect so that our respective device is being shown up. So this will be the device that we'll have to select. Once that is done, select this device. We'll change the SOF file for this, which will be saved in the output file LED counter. So that SOF file will contain the bitstream, which will be used by this application to program the FPGA board. So we'll have to click the program and configure and click start. So basically this will use the bitstream file or the SOF file and configures our FPGA as per our design. Once the configuration has been completed on the board, we can see that our respective design is working. Currently, I've set the direction toggle switch to low. So this is making the counter do a down count. So as soon as I press and release the reset pin, the counter will go to 0 and start down counting. As you can see, from 1111, now it has gone to 1110, and now 1101, and it proceeds to do a down count. And now it has reached 0. On down counting again, it went to 1111. Now let's toggle the switch to 1, which will make it as an up counter. I'll press the reset, so it will start from 0 and count up. So 0, 1, now it is 2, 3, and so on. And now it has reached 1111, and it will reset to 0 automatically. And in middle of the count, if we toggle the switch, it will immediately turn into a down counter. Now from 2, it will go back to 1, next to 0, and then 1111. So this shows that our 4-bit counter using a 32-bit pre-counter is working as required on the FPGA board. But this programming of the board that we did, it is just temporary, As soon as the power is disconnected, that program will be flashed from the board's memory. In order to make the design run on the board, um, even after a power reset, we'll have to burn the data into the memory or into the DE1-SoC's flash memory. So to perform the timing analysis of the board, we'll go to Tools, Time Analyzer. This will bring up the timing analyzer. So first, we'll have to perform update timing netlist, which will read the STC file and knows what our constraints are. Once that is done, we'll go to report Fmax. Fmax will report the maximum frequency our design will be able to operate, irrespective of our configuration um, or our constraints. So based on our constraint, irrespective of our constraints, our design is capable of working at 390 megahertz. Now, to understand the how it is able to work at 390 megahertz, but yet it is working at 50 megahertz due to the board's clock of 50 megahertz, we'll have to go to timing netlist, report timings. In the clock, we'll just select, fill up these details and targets. So here, since this is a synchronous circuit, our critical path will not be from input port to output port, but it will be in between two registers or two flip-flops, which has the biggest combinational circuit. So we'll just mention get the registers data, and even for 2, we'll mention it as get the registers data. We'll ask it to report based on the setup time, and we'll ask it to report the one path which is the highest propagation delay, and we'll just click report time. So this will analyze the design and mentions which is the path which has the highest delay or the highest slack. Here slack, the data that we'll have to look at is the slack and the nodes which are contributing towards the critical path. Here slack is mentioned as 17.442 nanosecond, and it is from precount 10 precount bit 10 to precount bit 28. Slack represents how much difference is there between the critical path's actual time for completing a task to our targeted completion time. Since our clock speed is constrained to 20 nanoseconds, the slack we are getting is 17.4 nanoseconds. That means our design is overperforming and is being idle for 17.4 nanoseconds. The same thing can be seen here in the waveform. So here you can see once the latch is activated, the clock delay is 3.89 nanoseconds and the data delay is 2.99 nanoseconds and is idle for the remaining time. So even though the data has already arrived at this point, and after that it is just idle waiting for the latch to grab the data. By doing this RTL design and configuring it onto our FPGA board, we accomplished to design a 4-bit up and down counter using a 32-bit precounter and configure the same to our FPGA board and flash that configuration or the bitstream to the board's flash memory, wherein even on power reset, our design will continue to work on the FPGA board.